Hello, good student. So today we want to look at derivative as a function. In fact, we want to look at derivative from the geometrical point of view. That means, suppose somebody gives you a graph of a function which is f of x, just the graph. We want you to be able that from that graph to be able to draw the graph of the derivative. So by looking at the graph and the behavior of the graph throughout, and then you should be able to draw the graph of the derivative by the end of this lesson. The second thing I want to talk about today is differentiability. By the end of the lesson, we should have defined differentiability and then connect it back to continuity. And the last thing which I will highlight is higher order derivative, including notations of derivatives. Now, without any waste of time, let's get there. Let's get there. Remember what we know. We have learned that the derivative at a fixed point A, is defined by this expression. We even said the same expression can define the slope of a straight line. What's that mean? It means if we have the slope, the line of a tangent being defined by mt x plus c, then the slope of this line, which we'll call it y prime, will be nothing but mt, which is the slope of the tangent line. This is very good because what does it say? It says something which we are going to look at here, that if you look at your straight line here, which is just nothing but, we call it yt, then we know that the slope of this line, which is y prime of t, or the derivative of our function which is y, which you can call it is f of x, which is just a straight line in this case. So we know that the slope will be just nothing but m. And the way I've drawn the line in this case, it looks like our slope now is positive. That means the slope is greater than 0. That's one thing which you should take today. And look at here. Now we want to move from a fixed point and then now define the derivative at any point, so that we can be able to now look at the function that describes the derivative here, and then talk about this as a function which defines the values of the function at any point x. At any point x. That's what we are going to talk about today. So, if you come to this case, back to our straight line here. So, if you want the derivative, you get this point. So what does it mean? It means f prime of x in the case of a straight line is nothing but m, and according to the way I've drawn it, it means our m is greater than 0. So it means if I want to draw the graph of f prime of x, it means my f prime of x, regardless of the value I take for x, f prime of x will be just constant m. So we know that it's positive, so let's assume that this is our m. If it's our m, that will mean the straight line is just there, which describes f prime of x at any point. That's in the case of a straight line. This is what we are going to deduce as we go along. You'll see we'll deduce the graph of f prime of x. That's what we want to end up knowing. So suppose somebody gives you another straight line which looks somehow like that, which we can call it y2, and then you can even define y2 to be m2 of x plus c2. So in this case, you can see that our m2, which is the slope of the second line, the way I've drawn this graph is less than 0. And if it's less than 0, it means now in this case our f prime, let's call it f prime 2, let's call it f prime 2. So our f prime 2 of x will be equals to nothing but m2. Will be equals to m2, and then suppose, and we know that m2 is less than 0, so suppose somewhere here you have m2, and then if we have m2, the graph of f prime of x will be just this line, this straight line, but which is below the x-axis, because now m2 is negative. That's a take home. So think about that, and then imagine we are dealing with just a straight line now. So looking at a straight line, we can be able to estimate, if somebody gives a straight line, we can be able to estimate how the derivative of that straight line will look like. But imagine now when it becomes a curve. That means the value of the function changes at every point. Even the slope changes at every point. That's what we want to get into now. So given any point x for which the limit exists, we know that we can assign to x some new value f prime of x. And we can regard the f prime as a new function called the derivative of f. It's just a new function which you call the derivative of f, which has a domain, and then the domain may not necessarily be the domain of f. It may be restricted, but that's the new function that we have. Now we are done with the straight line. We move a step further and look at a curve. Let's look at a curve. So suppose the graph of f is given right here. Now use it to sketch the derivative of f prime. Let me give you just 5 minutes to sketch the graph of the derivative of f prime. That means the graph of the new function, which is the derivative function. So sketch that graph before you move to the next step, and then once you have done your sketch, now you can be able to move to the next level, and then we look at what happens together. So what happens? So since now we are dealing with a curve, the best way to approach this part is to look at each point. So suppose we start with the point A here, and then we draw a tangent line, and then from that tangent line we are able to find the slope, which is m. So suppose in this case we find -1. So what does it say? It says at that point A, so suppose at that point A is defined by it is defined by A1. Let's say it's defined by A1, comma, -1. Oh, A1, comma, let's say that point is defined by A1, comma, f of A1. F of A1, which we don't know what it is. But now, if you take the derivative at that point, you get a new value. remember you are still at x which is equal to a. So you get a new point which is called a prime. Because our slope is negative, we are sure that the point that we are going to plot for the derivative function is going to be negative in this case because the slope is negative. So it means a prime, which is the point now which we are looking at here for derivative, will be a1 comma minus 1. And this point is on the graph of f prime. So it's on f prime of x. While the top point is on f of x. At the top there. And you can move to the next point. When you get to the next point, because around here you can see your function looks like your function is going towards 0, which we can say is decreasing, so the slope will remain negative. But at this point B, you can see your curve now flattens and it becomes horizontal. When you try to draw the tangent line, you get the horizontal line there. Now, since this is the horizontal line, we know the slope will be just 0. So that means that line is defined by nothing but y, which is equal to c. The slope is 0. So at that point B, where the slope is 0, we can define the coordinates of B prime, which we're interested in. We can define the coordinates of B prime being, let's say the x point is a2, then B prime will be 0. We've got the second point. Definitely, we've got the second point of f prime. And after that point B, you can see that now your slope, if you draw a tangent line somewhere around here, the slope will be positive. So for argument's sake, let's say the slope is just 1. The slope is just 1. So it means at C, our slope will be C prime. At C, we have the slope with A3. The slope, which is the value of the derivative function now, will be 1. So you can keep going on, and then you get to D, the graph becomes horizontal again, and then you are able to get, when it's horizontal, you know your slope is 0. That means now you have a D prime, which is the value of the derivative function. You have a4, but the value of y is 0. That's why our graph here for derivative is just at 0. It's crossing the x-axis. And also remember at B prime, we said the slope was 0, so our graph is 0 here. But at A, we said it's negative, so we know it's below here. At C prime, we said the slope is 1, so you can see that the value of the derivative function is positive. You can keep going on, and then you go to the next point, you get the negative value, you're below the x-axis, and then you can continue all the way until your curve again is about to flatten again here, where the slope now will get closer and closer to 0. That's how you draw the derivative function. So you're going to think about tangent line as many as possible along that graph. But since in some cases you'll find that the tangent line remains negative as long as the slope of this graph goes down. So it means as long as the graph goes down, the slope remains positive. Or as long as, later I'll say, as the graph is decreasing, the slope remains negative. And then as long as the graph now increases, the slope remains positive. So in that case, it makes it easier to just know or imagine the slopes of many graphs around that part where it is positive and around the part where it's negative. So you will be worried about the part where it is 0, and then here where it flattens out. You can be able to now reproduce this graph just going through those points that you have just plotted, and then you can see the behavior of the derivative function. That's it. So that's how you try to move from the graph of f of x and then be able to sketch the graph of f prime of x. That's what you are doing. Let's look at the next graph, probably trying to take the concept home now. Make sure that you get it. So let's look at another graph now. This is the graph of, if you look at this graph, is the graph of y, which is equal to the square root of x. We know that if we had y, which is equal to minus square root of x, we'll have another negative piece, the piece here which refers to the negative part. But now we only have the positive piece, so we don't have this portion. No problem. One thing to take is the behavior of this graph. Let me plot the behavior of the graph outside here. So the behavior from 0 of the graph, it comes steep, and then it starts to a little bit flattens. And if we had 0 here, and then you try to draw the tangent line, that means you try to draw the tangent line somewhere here at 0. You'll find that that tangent line, the slope of that line is so big because now it's almost vertical up. And if it can get vertical up, the slope approaches infinity. So that's why at close to 0 here, this is the graph of the derivative of f of x. Close to 0, you can see that the value of the derivative function is so big. It goes to infinity. It becomes so big. Now you go and draw the next tangent line somewhere here. You can see that now your slope, your straight line is flattening. Your tangent line, another tangent line somewhere here. You can see that your slope is getting smaller. So the slope of this graph now, it gets smaller. So as you move away from 0 on the graph, the slope gets smaller. So the graph started with a large slope closer to 0. As we move away from the 0, the slope gets smaller. And if you continue on the graph, you'll find that you draw another tangent line here. The slope flattens again. You draw another tangent line on this one, which is more clear. The slope flattens again. That means the farther you go to 0, the graph of the derivative gets closer and closer to 0. Or the slope of the graph gets smaller at those points. You draw another graph here, far it flattens. Close, it approaches 0. You draw another graph somewhere here, you can see the slope of this graph is going to flatten. So you are getting closer and closer and closer to 0 as the x goes to the values of x gets larger and larger. That's how you get the graph of f prime of x being given the graph of f of x. Just looking at the graph. If we were to find the derivative of this function, even from the first principle, you should be able to get this f prime of x being equal to this one, and then you should be able to get the graph of this one. So, what we want from you, we want you to be able to draw geometrically, not plotting points. Just look at the graph of the function and then sketch the graph of the derivative straight away. That's what we want you to know. We'll keep repeating it until the concept is home, with many examples that we'll meet in future. Let's look at the notations of derivative that you'll meet most of the time. You have already met that we can use f prime, and a little bit I introduced dy dx. Sometimes people will write y prime. Or sometimes people, instead of saying dy dx, since you are saying y is equal to f of x, they can say df dx. Or sometimes they can use a big D and then leave our notation in this form. So that's our notation. And the symbol and dy are called differentiation operators. So we are saying it's an operator that acts on f. Once it acts on f, we get a derivative function. That's an operator That's one thing which you should know. And you can see now we start to talk about the differentiation now, which is taking us somewhere to another concept which we'll define later. So the symbol dy dx is normally named after the guy, is it Leibniz? So you can look for this guy and then enjoy what he has done. And the notation of dy dx, it says if we have some average, we can take this thing as average change, and then now we are looking for instantaneous change where we look at dx as dx goes to 0. If we're talking about derivative, we'll say as h goes to 0, because our h also can be defined as nothing but delta x. So as it goes to 0 now, you get dy dx, which is the derivative of the function. So we have already talked about the derivative of a function, but one thing which is very important is that sometimes we, after getting the derivative of the function f prime, for instance, let's say you get f prime to be 2x, we may be interested to evaluate the value of f prime at a point, let's say 1. Then we'll find out at 1, the value of the function is just 2 times 1, which is nothing but 2. So to denote that we want to evaluate this value after finding the derivative, most of the time we'll say find the derivative f prime of x, and then we make a line here, and then we say after finding the derivative, evaluate that derivative at a point x which is equal to 1. So once you see this notation, it means after getting the derivative, you need to evaluate the derivative at that point. Sometimes we can say find dy dx, and after getting dy dx, evaluate that derivative at x which is equal to a. That's what you'll see most of the time, which is some kind of a notation that we'll use. So now we said now we can talk about when do we say a function is differentiable, which is somehow the last part that we wanted to discuss today. And then we'll just give a notation of higher order derivative. So a function f is differentiable at a point a if f prime of a exists. That's good, but it's still hard to imagine. But remember, f prime is at a just nothing but the slope of the tangent line. So if we can find the limit of that function, then we find that it exists, then it means the function is differentiable at that point. And we can even go further and give you a lot of work to say it is differentiable at an open interval, which could be this interval, or it could be another interval, many open intervals here, if it's differentiable at any point in that interval. So you need now to test any point in that interval. Example. So let's look at this one as our example. And the question is, where is the function f of x which is equal to modulus of x differentiable? But remember, we said it will be differentiable at a point if f of a exists. That means if f of a exists, then we can say this function is differentiable. Okay. So one thing that we know about the behavior of this function is a modulus function which can be divided into pieces where x is less than 0 and where x is greater than 0. So where x is greater than 0, we can just leave it as x. And what we do now, we can try to find the limit, which is the derivative for that case where x is greater than 0. Remember, when x is greater than 0, the modulus of x is nothing but x. So If we want the modulus of x plus h, it will be nothing but x plus h. In this case, we have assumed that x plus h is greater than 0. And then we know that the modulus of x will be nothing but x, because x is greater than 0. So you subtract x, x cancel, you're left with h over h, and then h cancels, you're left with just the limit of 1, which is nothing but 1. Ooh. And then we can conclude straight away that, so f is differentiable for any point that is where x is greater than 0. So wherever x is greater than 0, our function becomes differentiable. But we haven't finished. Remember, now we can have another case where x is less than 0. What happens? If x is less than 0 now, we know that the function becomes, the modulus of x becomes minus x. Or, since x is less than 0, give it a minus sign so that the whatever comes out of the modulus remains positive. And we can do again to say the x plus h also to be small, to be less than 0. So we are choosing h to be so small that x plus h remains negative. If you do that again, the modulus of x becomes nothing but, in this case, it becomes minus x plus h, and then the modulus of x becomes nothing but minus x. We can simplify that, the x will cancel, and then we're left with minus h over h, and then we end up with minus 1. Interesting. So again, we can conclude here that f is differentiable for any point where x is less than 0. But there's still a problem at around 0, if we can see here. There's still a problem around 0. So we need to test, because we have tested greater than 0 for x which is greater than 0. Now we have tested when x is less than 0. Let's test at 0 and see what happens. Let's investigate around 0. So for when x is equal to 0, now we plug in. Remember, previously we left it as x plus h, but now we know that x is 0, so we can straight away plug in 0. Then we have f of 0 plus h minus f of 0. So remember, f of x is defined as nothing but the modulus of x. So whenever it's 0 here, you get 0 here. And then if it's 0 plus h, you get nothing but the modulus of h. So when you are here, you don't know how to conclude here. You have modulus of h over h. The best way to go about this problem is to look at sided limit. So let's start with sided limit. So let's start with the approach 0 from the left. If you approach 0 from the left, we know that in this, or from the right, we know that in this case our h is greater than 0. So we can leave the modulus out. Then we have this part, and then we end up again having 1. You consider another case when you approach from the left. If you approach from the left, you know that now h is negative, so to keep it positive, we apply the minus sign. Then we end up with minus 1. Now we get two different limits. From the left, we get minus 1. From the right, we get 1. We can conclude that this function is not differentiable at 0, because now the limit does not exist. That's what we are saying. Since the sided limit are not the same, therefore we can say f prime as 0 does not exist. Thus, we can even conclude that f is differentiable at any point except at x which is equal to 0. Interesting. And we have already found that f prime of x is 1 when x is greater than 0. We also found that it's minus 1 when x is less than 0. So you can plot that function and then leave just at 0. At 0, we concluded that it's not differentiable. So when x is less than is less than 0, then we have this piece which remains at minus 1 of f of x, and then at 0 there is a jump, you jump, then when x is greater than 0 you have that piece which remains at 1 all the way. That's what you have. But remember, we talked about straight lines at the beginning. We talked about straight lines. We even concluded that looking at just this graph, we know that this piece, which is on the positive part, which you can call it, the slope of this line, call it m1, will be greater than 0. That's why this time we have 1. So that slope is just 1. And then we also concluded that if we have this piece which is decreasing now, we know that the slope of this line will be, which will be m2, this piece will be less than 0, which is nothing but in this case minus 1. That's what we did, that we can have those pieces here and then the other piece there at the top, except at 0. At 0 we said the function is not differentiable. So that's what we see. What we see geometrically at 0. What you see geometrically at 0. One thing which you can suspect, you can see our function comes closer to 0, but when it gets to 0 there is a sharp point there. We may suspect that because now the graph has a sharp point, that's why the function is not differentiable. That's our suspicion. So we can now bring continuity and differentiability together now with this theorem. If f is differentiable at a, then f is continuous at a. In fact, if we take this statement to be P, and then you take this part of the statement to be Q, what we are saying P implies Q in this case. So it means if a function is differentiable at a point, then we can conclude that that function is continuous. If somebody asks you to prove that the function is continuous, and then you are able to test differentiability easily, you can conclude that that function is continuous. But the converse is false. That means you can't say Q implies P. That means if the function is continuous, it doesn't mean that the function is differentiable. That is wrong. We cannot conclude anything. That's why we are saying the converse of this theorem is false. It's not always true. It may be true in one case, but it's not. It doesn't mean automatically that once the function is continuous, it will be differentiable. But we know for sure if it is differentiable, it will be continuous. One thing which you learn with these statements, even those who are doing logic, they will tell you that this statement is equivalent to say not Q implies not P. So what does it mean? It means, in other words, if the function is not continuous, it's definitely not differentiable. Those are the two equivalent statements. So if the function is not continuous, you can conclude that it's not differentiable. But if the function is continuous, you cannot conclude that it is differentiable. You won't come to this temptation. But if it's not continuous straight away, you can conclude that it's not differentiable. Back to the graph. If we can test continuity around this point, check if the function is continuous around that point. In fact, you'll find that it fails because we have already found that the decided limits are not the same. So the function is going to fail to be continuous at that point, and we can conclude that it's not differentiable at that point. That's one way to test. So what are we saying? We are saying we saw that the function f of x, which is t equal to that, is not differentiable at 0. And then we have seen that the function becomes very sharp. If you look at the graph of the function, it becomes very sharp around 0. And then some people call it the graph has a corner, or just like a corner of the house. It's very sharp, or it has a kink. And so some people will say it has a kink there around that point. And once the function looks like that, it's not differentiable. In fact, if we can meet a nice function like this, we call it to be smooth. So this one would be differentiable at any point because it's very smooth. Except if I make it steeper. If I make the slope steeper, there are a lot of problems that may come there, especially around the steep part here, as we can see in the next part. So, when do we say there is a possibility of function not being differentiable at that point? That's when you have the vertical tangent line. That means the function becomes steep. And at that point, we agreed at the beginning that the slope of that function will be approaching infinity. So at that point, we need to be very, very careful. Here is the graph of the function. Look at the graph of the function. The graph of the function here gets to be sharp around this point. Very, very sharp. And then not only sharp, but as we approach the point, the slope becomes definitely somehow vertical. And then look at the behavior of this graph, which looks somehow like that. At this part, the slope of the graph now approaches infinity. Or this means the tangent lines become steeper and steeper, or the slope of that tangent line becomes large. So at that point, we have another case where we can say there's a possibility where the function can fail to be differentiable. Other cases are here. Here we've already talked about a corner or a kink, and then where you have a jump discontinuity. We know that once the function is not continuous, we can conclude that it's not differentiable. Even a case where we have a steep tangent line with a very big slope, So the slope of this graph approaches infinity, or of this straight line. What are we talking about? We can finish this part of the lesson by just highlighting that we can even go further with derivative. We can start talking about second order derivative, where we have the first order here. Then we can introduce the derivative over derivative to get a second order derivative here. That means now you're taking derivative of the derivative. So you can do that, and you'll see that if we have this function, the first derivative becomes this, and then you take the first derivative, you take derivative again of that derivative, you continue here, you end up with 6x here. Looking at the graphs, let's look at the graph. So this is f of x, and then if we look at this graph, although this graph here has some negative values, but if we draw the tangent line around here, you'll find that the slope is positive. That's why around that point you have the values of the slope being this side, which is f prime. So when we get somewhere here, you can see that the slope are getting closer to 0. The values of the function are getting closer to 0. In fact, if it becomes flat somewhere here, you are right at a point 0 here, where f prime crosses 0. And then you continue again, somewhere around here, you can see that your slope now is negative. Somewhere here you can see that your slope is negative. That's why the values of the functions now, they're a bit negative. And then later the slope start to increase to be, once it comes like that, it gets to be positive. Now the value of f of x becomes that. If you find the derivative again of f of x, you end up now with a straight line. this straight line that you see here. So that's the straight line that we end up with. I'm leaving you on that one. You will digest it as we have done previously and then make sense of that. So we have already talked about second order derivative. We can even introduce third order derivative, where third order taking the derivative of the second order, and then we have this notation of the third order. In fact, we can talk about the nth order derivative. The nth order derivative can be represented by yn or fn of x or dy dx, dn y dx. So we can see that our n here is somehow like the superscript of d and then over dy. So that's what you should take home. So you can do derivative of another derivative step by step. Derivative of the first order of the function, you get the first order derivative or f prime, and then you take the derivative of f prime, you get f double prime. But you cannot keep doing prime, which will take too long. So we can say f superscript 2, superscript 3, that means f triple prime. And then you can continue up to fn of x, as we see here. So this is where we stop. It was quite a long lesson, but now what should we have learned in this lesson? The first thing which you should grasp is the concept of derivative geometrically. What do you mean by geometrically? Somebody gives you the graph of the function, you should be able from the graph of the function deduce the graph of the derivative function. At least even if you don't draw, you should also have that concept in your mind that the graph of the derivative function around this part of the graph of f of x will look like this. Should have that. The second thing that we introduce is differentiability. We introduced the theorem about differentiability, and then we showed that if the function is differentiable, it implies that that function is continuous. If the function is differentiable, then the function is continuous. We noted that the converse is false. That means if the function is continuous, it doesn't mean that the function is differentiable. It may happen, but it doesn't mean that the function is differentiable. The last thing that we learned the convex. What did they call it? Contrapositive of that part of the statement, that if the function is differentiable, then we said it is continuous. Then we said the same statement can be equivalent to if the function is not continuous, then the function is not differentiable. So if you are about to test differentiability, you may try to test continuity and you find that the function fails to be continuous. You don't need to go further and test differentiability. You can conclude straight away that since it's not continuous, then the function will not be differentiable at this point or in this interval. That's what you should have learned today. So this is where we stop. Let's meet this Friday on tutorial, and we'll meet again next week with some lectures. So I have uploaded another material where there are rules of derivatives, so you can go through that fast. But this concept, that's the one which I wanted to talk about today. So look through how to use the power law, product, and many other rules of derivative, which makes it easier. So we focused more on the concept of finding the derivative from the definition which we used to give students a problem. But I know the other ones used to be very easy, where you just find derivative algebraically. So let's stop here and good luck.